California just removed 4 dams in 1 year. 4 massive walls of concrete, gone. And what happened next, nobody could have predicted. For over 100 years, this river was basically dead. 100 years ago, they built these dams to make electricity. But in doing that, they trapped an entire river. Fish couldn't swim upstream. Water turned toxic. An ecosystem that thrived for thousands of years just stopped. Then in 2024, something historic happened. Crews tore down all 4 dams. J.C. Boyle, Copco 1, Copco 2, Iron Gate, gone. This became the largest dam removal in the history of the entire world. But here's the crazy part. Nobody knew what would happen when they let the water flow free again. Would the river even survive after a century of being choked? Then the salmon showed up. Thousands of them. Swimming upstream into water they hadn't touched in 100 years. Scientists watched in real time as a river everyone thought was gone forever came roaring back to life. But this comeback comes with a warning nobody's talking about. So what actually happens when you set a river free after 100 years of captivity? And is this a miracle or the beginning of a whole new problem? Long before concrete walls blocked its path, the Klamath River carved its way from the high desert lakes of southern Oregon down through the steep mountain canyons of northern California, running roughly 260 miles to the Pacific Ocean. This cross-border basin was once the 3rd most productive salmon watershed in the United States, defined by a clean, free-flowing system that sustained local communities for thousands of years. For the indigenous nations of the basin, the river was an ancestral relative, central to daily life. Salmon served as food, ceremonial lifeblood, and the primary measure of the river's health. But each tribe held its own distinct relationship with the water. The Yurok tribe, situated at the river's mouth, and the Karok tribe, managing the middle reaches, developed separate, sophisticated fisheries and cultural ceremonies tied to the seasonal runs. Further inland, the Hoopa Valley tribe focused on the key tributary of the Trinity River, while the Klamath tribes in the upper basin in Oregon held treaty-protected rights to the headwater fisheries. Historical records and tribal testimonies describe a river so thick with migrating fish that the water seemed to boil. Salmon ran by the hundreds of thousands, bringing ocean nutrients far inland to the mountain forests. The seasonal arrival of the Chinook and coho determined the health, wealth, and spiritual calendar of the basin. The relationship was reciprocal. If the people took care of the river took care of them. This delicate balance endured for millennia, anchoring an entire region's survival to the pulse of the flowing water. In the early 20th century, a new vision of industrial progress reshaped the American West. Hydroelectric generation operated on a straightforward principle. Gravity pulled water down from high elevations through massive steel pipes, spinning turbines to convert that controlled flow into electricity. As logging operations expanded and mining camps grew into permanent towns, the demand for reliable energy surged across Northern California and Southern Oregon. Local newspapers and the California-Oregon Power Company championed these projects, promising that taming the wild river would bring modernization, light, and enduring prosperity to the high desert. The engineering effort began in earnest, with the construction of the first Copco Dam in 1918, followed by Copco 2 in 1925. Decades later, the system expanded upstream with the J.C. Boyle facility in Oregon in 1958, and concluded downstream with the Iron Gate Dam in California in 1962. Managed first by the California-Oregon Power Company and later by Pacificorp, this 4-dam network generated a combined capacity of approximately 163 megawatts of electricity. Importantly, these structures were built solely for power generation, operating completely separate from the federal government's nearby agricultural irrigation project. For decades, the constant hum of these turbines represented the mechanical heartbeat of regional growth. The physical restructuring of the Klamath began the moment the concrete dried. By blocking the main channel, these structures completely severed the biological highway of the basin. For migrating salmon, even a single barrier meant a permanent dead end, trapping fish downstream and rendering over 400 miles of upstream spawning and rearing habitat completely inaccessible. But the physical barrier was only the first link in a chain of physical changes. A natural river relies on its thermal regime, the natural seasonal pattern of water temperature that signals when fish should migrate and spawn. The dams disrupted this entirely. In place of a swift, cooling current, massive volumes of water sat stagnant in deep reservoirs. This slower, layered water absorbed summer heat, raising downstream temperatures and delaying the river's natural autumn cooling. At the same time, the structures began trapping the very foundation of the riverbed. A healthy river constantly carries gravel, sand, and organic soil downstream. This material was caught behind the concrete walls, causing severe sediment starvation. Below the dams, the starved riverbed became hard and eroded, stripped of the loose gravel salmon need to construct spawning nests. Within the stagnant reservoirs, water quality deteriorated as the natural current died. Lacking physical movement, the water became stratified, trapping cold, oxygen-depleted layers at the bottom while heating the surface. These warm, stagnant conditions fueled harmful cyanobacterial blooms, creating measurable water quality risks and increasing disease pressure downstream. As independent hydrologists observed, this altered flow disrupted, dissolved oxygen and created localized pools where lethal parasites multiplied, turning a free-flowing river system into a series of predictable hazards for migrating fish. On September 19, 2002, the river's simmering crisis broke. Along the lower channel, the water turned brown as approximately 34,000 adult fall Chinook salmon floated to the surface, dead. While elevated temperatures and pathogens like Ichthyophthirius and Flavobacterium columnare ravaged the crowded fish, federal investigators identified low river flow as the primary controllable cause. For tribal members, commercial guides, and river-dependent businesses, this massive die-off shattered local livelihoods, devastated coastal fishing economies, and violated long-standing treaty expectations, instantly turning ecological grief into intense political outrage. The disaster forced immediate negotiations, colliding with PacifiCorp's 2004 relicensing pressure. What followed was a decades-long institutional battle. Water management, agricultural irrigation demands, power generation, and fish survival pulled federal agencies, basin farmers, and tribal nations in opposing directions. Though stakeholders signed the Klamath Hydroelectric Settlement Agreement in 2010, localized funding problems and complex legal disputes dragged on for 12 years, delaying actual implementation. It was not until November 2022 that the Federal Energy Regulatory Commission finally approved the surrender of the lower project license, transforming a catastrophic biological failure into a historic, binding legal mandate. The execution of this legal mandate fell to the Klamath River Renewal Corporation, a nonprofit created specifically to take over and dismantle the 4 aging structures from PacifiCorp. Working with contractor Kiewit Infrastructure West, they converted the settlement into a massive multi-site engineering campaign. Spanning the Oregon-California border, this operation was the largest dam removal in world history, a claim measured by the demolition of 4 major structures and the reconnection of roughly 420 miles of historic salmon habitat. This scale far surpasses the landmark Elwha River project in Washington, which removed just 2 dams to reopen 70 miles of river. The physical sequencing began in June 2023 with Copco 2 in California, a 33-foot concrete diversion structure. Because of its smaller size, crews cleared this first barrier by November 2023, testing sediment management plans before tackling the larger reservoirs. In January and February of 2024, engineers initiated reservoir drawdown, slowly releasing millions of gallons of water to expose the foundations of the remaining 3 dams. Each structure presented distinct challenges. In Oregon, J.C. Boyle was an earth-filled dam holding the system's largest generating capacity of 98 megawatts. Downstream in California lay Copco 1, an early concrete gravity arch dam built in 1918, and Iron Gate, a towering 172-foot-tall earth-fill structure that stood as the lowest barrier on the main stem. Crews used temporary cofferdams to divert the river, allowing heavy equipment to systematically dismantle the concrete walls and earth embankments. On August 28, 2024, explosives and excavators breached the final cofferdams at Iron Gate and Copco 1. By October 2, 2024, crews cleared the very last obstruction, restoring a free-flowing river and ending more than a century of blocked upstream access. For the families living along Copco Lake, the emptying of the reservoir felt like losing a member of the community. Longtime shoreline resident Danny Fontaine described the water as the very heart of their neighborhood, while his neighbor Kevin Feltz recalled the lake as a magical place of boating, fishing, and shared summers. The draining of the basin erased familiar property lines and dissolved a century-old regional identity. Some residents, like Francis Gill, worried that removing the water would disrupt land surveys and historical coordinates. This physical shift also renewed anxieties about regional resources. The 4 dams had provided steady employment and generated enough electricity to power thousands of homes, though Pacificorp representatives noted the loss represented less than 2% of their overall system. While utilities replaced this capacity with wind, solar, and gas, local farmers faced immediate uncertainty. Although the dams were separate from the federal irrigation project, agricultural groups worried about water reliability during dry seasons, calling for assurances that crop deliveries would not suffer. Project planners, including demolition manager Mark Bransom, maintained that the phased drawdown was necessary to manage sediment safety and lower hydraulic pressure. In the face of these competing interests, success in 5 years remains an open question. For conservationists, it means healthy salmon runs, but for local landowners, it requires finding a new future on the dry banks of a vanished lake. As the water drained away, it left behind a vast gray moonscape of wet mud. Beneath the former reservoirs lay decades of accumulated lakebed material, an estimated 3 million tons of fine silt and clay. Computer models had predicted that the bulk of this stored sediment would mobilize during this first year, but as the river began cutting through the muck, field hydrologists watched to see if reality would match their math. What followed was a series of thick, muddy, flushing flows. High-velocity currents tore through the newly exposed channels, triggering rapid erosion and sending plumes of suspended fine material downstream. Along the banks, crews raced to install stabilization measures and plant native seeds to hold the fragile earth in place. As the river sliced deeper, it exposed long-buried history, relict river channels, ancient floodplain layers, and century-old cultural artifacts. This massive pulse of mud represents a delicate ecological trade-off. While the sediment can smother vital spawning gravels in one reach, it can build essential habitat in another. For now, the river is in a state of violent transition, caught between short-term chaos and the slow, uncertain work of carving a permanent path home. In October 2024, just days after the final concrete barrier fell, the first biological signals flashed through the monitoring networks. Biologists from NOAA Fisheries, the U.S. Geological Survey, state wildlife agencies, and university partners deployed a wide-ranging tracking grid. Using underwater sonar, pit tag detectors, radio telemetry, visual counts, and carcass surveys along the newly opened main stem, researchers watched the river's response. Alongside tribal monitoring teams, they waited to see if the fish would find their way home. This monitoring effort represented one of the largest tracking campaigns ever designed for a river restoration, checking every bend across state borders. The response was swift. In late 2024, adult salmon began crossing the threshold of the former Iron Gate Dam site. One early monitoring account recorded more than 7,700 individual fish passing through the newly cleared channel, with approximately 96% identified as Chinook. These were far more than brief sightings. Crews tracked fish migrating past the former barriers, documenting active spawning evidence in gravel beds that had been buried under reservoirs for decades. Some detections occurred more than 360 miles upstream, proving that the fish could reach the headwater tributaries of the upper basin. Still, federal and state scientists urge caution. Jim Simonday of NOAA Fisheries notes that these initial figures represent early counts and localized detections rather than a complete basin-wide census. This biological return coincided with rapid, measurable improvements in water quality downstream. Tribal monitoring, paired with automated instrument-based testing, showed the toxic legacy of the stagnant pools was fading. Josh Cahill, the water program manager for the Yurok tribe, documented a significant decrease in microcystin levels within the former reservoir reaches, confirming that the dangerous, warm-water blue-green algae blooms were losing their grip on the free-flowing river. Fish swimming past a former dam site does not guarantee a recovered population. Durable success requires decades of observation, measured in repeat adult returns, juvenile outmigration survival, genetic diversity, and stable water temperatures. The newly formed river channel will take 3 to 10 years to stabilize. While the banks settle, monitoring teams must watch for heavy metal bioaccumulation, legacy industrial contamination, and invasive species. Persistent regional drought and competing agricultural water demands remain constant pressures on this fragile system. The financial trade-offs are equally stark. The core project cost climbed toward $446 million, while the lost hydropower represented less than 2% of the utility's power portfolio, replaced by gas peaker plants, renewables, and regional imports. Different groups hold vastly different measures of success. Tribal programs, scientists, landowners, and farmers each look at this returning flow through different eyes. Whether this historic effort represents an environmental miracle, a fragile ecological transition, or simply the beginning of a new set of resource battles remains an open, unresolved question. The Klamath now flows free, but the true test of this historic experiment is just beginning. As the mud settles, we must redefine what restoration really means. Breaking the concrete was the easy part. Healing a century of ecological and human division will take decades. Can we truly undo our engineering mistakes, or have we just opened a new conflict? Share your thoughts below.